Thank you very much. I'm very honored to be here and speak with you today. I want to introduce you to Quine, the subject of our talk today. So I must be brief. There's so much to say, but thank you again for the opportunity to share what we've been working on. My name is Ryan Wright. I am the creator of Quine. I also lead a company called that provides enterprise support for Quine. And today's talk will be about the technology. So Quine, we'll talk about what it is, how it works, the new capabilities that it provides, and where it fits in. Quine is built entirely in Scala. We released it just a couple weeks ago as an open source project at quine.io. So it is free to the world and open to everyone. So I want to share with you what we've done. So let's ask this question: what is Quine? To start with, Quine is several things. And so we have to begin with disambiguating and talking about where this name shows up in more than one place. The Quine that we'll talk about today is a streaming graph. So it is meant for data processing in data pipelines in high volume situations. But you might have heard the term Quine before as a program that outputs its own source code. So a Quine just simply prints its own source code. Now, both of these things are named after the 20th century philosopher, Willard Van Orman Quine. So an American philosopher, very influential, did a lot of work in logic. And I tend to think of him as kind of the grandfather of functional programming. We have Quine to thank for coining the terms referential transparency and functor. And so these terms are in play because of their original philosophical use in the 20th century. So our project is named after Quine, but just wanted to be clear that there's already a name Quine that gets used in the world of computer science. So since they are both named after him, let's move on and talk about this particular Quine. Quine, this project is aimed at the problem of streaming data. And with streaming data, which a lot of Scala pipelines are built to enable, the goal is to take data and turn it into business value. And everything that happens in between that space is the job of interpreting that streaming data to answer the question, what does that data mean? So if we were to write out some requirements for this, we might say, well, we need to handle high volumes of data. It needs to run in rather low latency. We have to deal with the fact that there's limited RAM. It has to force us to use time windows within which to join data from different sources. And when you build a microservice architecture for that, you'll end up having to turn the database inside out to build that kind of a platform. You have to confront all sorts of CAP theorem trade-offs along the way and deal with problems of distributed transactions and order-dependent processing. And then in most companies, you'll have to set up a separate pipeline to replay data in case you need to debug your pipeline or need to produce a report from last week or some old data of that sort. So this is the world of streaming data, and it starts with this simple view of interpreting that streaming data, and it turns into a very complicated picture. The architecture diagram might look something like this. So it is complicated, but the good news is it is technically possible. And a lot of data engineers build large microservice architectures to do exactly this, to interpret streaming data. A lot of this is done in Scala. There's really excellent tooling for this. Functional programming is an excellent paradigm for doing that transformation and building a lot of these services, but they end up being a mess. And if you've ever run one of these services before, it's really only a matter of time before it goes up in flames and you realize this is really hard to do. It's error prone, it's slow, it's expensive. It's very hard to hire the right people and the right people who have the right talents. And if they leave, then you might be better off rebuilding your whole system. Nonetheless, this is the state of the art. And so the industry tends to say, well, we'll figure it out one way or the other. This is the problem we created Quine to solve. So Quine is the result of more than 7 years of research and development by teams at Galois and funded through DARPA and the US government. Quine is a streaming graph interpreter. And so what that means is it's aimed at that same problem. Take data, turn it into something valuable to the business. But then the typical trade-offs and expectations that we have a new perspective on those trade-offs. So still deal with high volumes of data and produce results with low latency, but now let's enable low RAM usage. Instead of having to continually scale up our use of RAM, enable using very little amounts of RAM. Let's get rid of this notion of time windows that you can only join data if it arrives within the 30-second window or a 5-minute window or how long that might be. Let's package the system back up again so that it's easy to use and to deploy and to run. Let's approach these CAP theorem trade-offs with some creativity that gives us new capabilities. Let's look at the data itself, using the data itself for our transactions. Let's handle out of order data and produce the right answer regardless of what order it arrives in. And when we have to go back and answer a question about producing a report for last week or an answer or debugging some old data, let's go query the past as it was at the time. These are the goals that Quine achieves. And I want to share more about how it's been done. Quine is a streaming graph. It means it really has two parts. The first part, data streams in and produces what we call event-driven data. So you connect Quine to something like Kafka or Kinesis, data streams in, and Quine builds that into a stateful graph, an internal stored on disk graph representation of the data coming through that stream. And then we monitor that graph live on the fly at a very high volume to produce what we call data-driven events. So when certain shapes appear in that data, the graph that we're building, we produce real-time results downstream to the next elements in the system. So this enables all kinds of functionality, everything from cybersecurity and graph AI to blockchain analysis, CDN log monitoring, monitoring an ops environment with Kubernetes and plenty of others. I want to focus in on one just to show a quick example. The cybersecurity case. Data comes in at the bottom of many different types. In the cybersecurity world, you're trying to put together a high volume stream of data that includes emails and users and computers and IP addresses and so many other things that are a part of the security landscape in an enterprise. And the goal of the data pipeline is to raise the level of abstraction and climb that ladder to make that high volume, low data more valuable and a lower volume that is more meaningful. And so over on the right, you see the obligatory XKCD. Oh no, we're going to analyze a bunch of data. Well, that'll just produce more data. The real goal of data analysis in the data pipeline streaming world is to take in that high volume data and interpret it into low volume data that is much more meaningful. And so this is the problem that Quine is aimed to address, is to do that interpretation live in the stream. So let me tell you how it works. Quine is built on a graph data model. Like I hinted at earlier, that graph data model, sometimes people think it is a different kind of data model, that some data fits in a relational model or a tree structure, but in truth, the graph data model is a superset. You can model everything in a graph that you could model in a relational table or tree structures or key value store. The graph gives you extra powers and is a superset of a data model for this. And so in a sense, the graph really is that master abstraction. Quine builds on top of the graph as the centerpiece of what we're working with. As data streams in, it is built into this semantic graph, where the graph structure models the data in much of the way that some languages in the world are organized with a subject-predicate-object relationship. In a graph, the graph can organize it as a node-edge-node relationship. And the nodes are the subject and object. The edge between them is the predicate. And so literally anything that you could express in natural language can be represented very naturally in a graph. So with a graph data model as the choice for how to represent the data that will be streaming through the system, we've built that on top of a graph computational model. So, and this is what Quine is unique at in that we've built on top of Akka this graph structured streaming graph just entirely on top of Akka, on top of the actor model. So under the hood, it's asynchronous message passing, single-threaded actors encapsulating their state. And one of those actors is behind every node in the graph. So when you need to stream data through to create structures or to query results and get them back out again, under the hood, Quine turns that into message passing between actors under the hood. As that data changes, messages are relayed to actors. Each node in the graph, backed by an actor, saves its data using an event sourcing strategy. So the node itself takes instructions as new data streams in, compares whether or not those instructions call for changes to state. If they do, the node will save to an append-only log on disk just the minimal delta required to do that. And this is how Quine is able to achieve very fast speeds, is that we don't have to save a lot of data and don't have to go back and forth to disk all the time. It can be streamed in and only the changes, only the deltas written to disk directly. So the event sourcing strategy under the hood helps, backed by Akka, helps Quine to be very fast and effective at data processing. And the graph data model helps it be very expressive. That data storage layer is backed by any of several different versions, any of several different tools. And so it supports Cassandra or RocksDB on the back end, as well as several other options. What Quine really needs from that is just a key value store. And the structure of the keys and values can take different shapes depending on the specialty of the particular data store chosen. So what does that give us? Under the hood, those are the typical capabilities that it is built with. And probably none of those are earth-shattering. The graph data model has been around for a while. Actors in Akka have been around for a long time and are well established. Event sourcing has been around for a long time. But when we put these things together, along with a few other creative approaches to how the system works, we end up with some very strong and powerful new capabilities. Starting with graph queries on a stream. High volume data streams in, and you can express queries on that stream using a high-level language like Cypher. Cypher is a graph query language. It's very close to SQL, except you draw something that looks kind of like ASCII art over on the side. To picture nodes and edges as a part of what you're searching for. And so you can express graph queries on a stream. We've written a compiler for Cypher that translates those into an abstract syntax tree relayed through the graph to each node in Quine. So express a graph query and you'll get that result back automatically. That gives you current results for the current state of the stream as it is up until this point. But we can also do queries in the past. Historical queries are a fairly easy capability for Quine. Since we are storing on disk the changes over time to every particular node, a query can come into the actors and include a timestamp that says, give me the answer as it was at this historical moment. And then each node can replay its history only up until that moment, compute its portion of the answer, and then relay the rest of the query through the graph. And so in this way, you can ask a question for what is the answer to my query right now? And what was the answer a minute ago, or an hour ago, or a month ago? Same query, just include a different timestamp, and you'll get the result as it was back at that historical point in time. And in addition to that, we have created a functionality that we call standing queries that allows querying the future. So we had graph queries on the present stream, graph queries in the past, and standing queries give us the ability to query the future. It's done by issuing just a normal ordinary cipher query that is dropped into the graph and lives inside the graph. The actors that make up the graph handle automatically propagating that query through the graph. They push it proactively to their neighbors. As new data streams in, it completes more and more of the pattern that we're looking for. And then every time there's a match for the pattern that our query is looking for, it streams out to trigger new results. So that match might be pushed out to the next item in the data pipeline, the next system in the data pipeline, or it could even call back into the graph and cause other side effects and update the graph itself. And lastly, this is how we banish time windows from our stream processing. No more limiting the ability to join data only if it's within a certain time window. Instead, let's join together the new data that arrived right now with data from months ago. And let's view the entire collection of the stream and the state it has produced as a single unit that we can compute over very quickly and stream real-time results out. I invite you to check out a demo of this system running. If there were more time right now, I would love to do a live demo, but in the interest of time, we'll move on past that. So I encourage you to check out this URL. I'll show it again at the end of the slides, but it is that.re/demo. And let me answer this last question then. So where does this fit into my existing systems, my existing architecture? The answer is anywhere that you have custom business logic as part of a data pipeline, any one of those red circles on the left-hand side, data streams through the pipeline and percolates through several different systems as it moves through the pipeline. One of those might be an excellent target to consider replacing or using or implementing with Quine. So Quine can consume from a data pipeline tool like Kafka or Kinesis, or files or many different options, and then stream results out to the next system in the pipeline. And then it can greatly simplify the custom business logic that has to be built. And so you can try it in one corner of a data pipeline or when adding one little bit of new functionality, and then consider maybe it would apply elsewhere in the pipeline as well. And you can gain the simplicity and the scalability of this system wherever it makes sense in your system and in your architecture. So to summarize, we think of Quine as really having these two sides: event-driven data. So consume a stream of events and build it into a graph data model that lets you focus on the shape of the data and not the order of operations to handle the incoming data. You can consume from many sources. It's fast and it's flexible, and it gives us the ability to eliminate time windows from the way we process streaming data. The second side of that is data-driven events. The structure of the data causes events to stream out of Quine and feed additional systems or to trigger other actions. This is a way to implement complex event processing using just a single database style query. You can trigger actions and update systems and even do computation inside of the graph itself. Our goal is to interpret high volume data. We want to turn that high volume data into high value data. That incoming data could come from many different sources, could be logs or metrics or alerts from existing systems. Streams through the graph is interpreted by running queries on the graph, by relating data to other data in the graph. And then every time there's a match found and produced, it streams out in real time to deliver answers or to trigger actions to other systems. With that, I'd be happy to answer any questions if we have time. And I would invite you to check out quine.io. So it's an open source project with a website full of documentation and getting started tutorials. You can download Quine. You can follow the links to the GitHub and see the Scala code on GitHub. I encourage you to download it and try it out. We've had a bunch of users lately asking really interesting questions about considering reinforcement learning applied on top of this inside the graph, or many other different interesting use cases for starting to implement graph AI or other applications. So the link for the demo is down in the bottom right corner, that.re/demo. Thank you very much for your time and your attention.